Hello everyone, let me introduce myself to you all. Myself Govindaraman, currently pursuing my degree in computer science and engineering with AI as my specialization in Sri Venkateswara College of Engineering. So my presentation is about quicksort and its time complexity derivations. Coming to table of contents. Firstly, we'll be studying about the introduction part. Second, what is sorting and its types. And third, we'll be studying about quicksort and algorithm for quicksort and a basic example for quicksort and time complexity. And lastly, we'll be getting the conclusion of the overall presentation. Firstly, the introduction part. Quicksort is a popular sorting algorithm based on the divide and conquer approach developed by Tony Hoare in 1960, widely used for its efficiency in practice. In this presentation, we'll explore the working principles of quicksort and analyze its time complexity. Coming further, what is sorting? Sorting refers to the process of arranging data in a specific order, either in increasing or decreasing manner, based on some linear relationship among the data item. The most common uses of sorted sequence are to make lookup or search efficient, to make the merging of lines efficient, and to enable the processing of data in a defined order. The opposite of sorting is shuffling, which refers to rearranging a sequence of items in random or meaningless order. Moving further, types of sorting. There are various sorting algorithms designed to perform this task, each with its own advantages and disadvantages in terms of time complexity and efficiency. Some popular sorting algorithms include bubble sort. So basically, bubble sort is it repeatedly steps through the list to be sorted, compares the adjacent elements, and swaps them if they are in wrong order. Second is selection sort. It selects the minimum or maximum element from the list and moves it to the front or back until the entire list is sorted. Third is the insertion sort. It builds a sorted array one element at a time by repeatedly inserting an element in the correct position within already sorted position of the array. The fourth one is merge sort. It employs a divide and conquer strategy, recursively dividing the list into smaller sublists, sorting them, and then merging the sorted sublists back together. And the fifth one is quick sort. Also uses divide and conquer approach. It selects a pivot element, partitions the list into elements smaller and larger than the pivot, and then recursively sorts the sublist. And the sixth one is heap sort. It uses a binary heap data structure to sort elements effectively. So basically, the choice of which sorting algorithm to use depends on the size of the data, the distribution of the data, and the specific requirements of the application. Sorting is a critical operation in computer science and is an efficient sorting algorithm is essential for many practical applications. So mainly we'll be talking about quicksort. As the name suggests, this algorithm is a quick or fast in terms of speed, and this is one of the reasons why it is so famous. This algorithm is based on divide and conquer approach of programming. If you are familiar with merge sort, then you may know what this approach is. And if not, don't worry, I'll explain it in brief. The divide and conquer approach involves dividing a task into atomic subtasks and then solving those subtasks. The result of those subtasks are then combined and evaluated to get the final result. Let us now discuss how the approach applies to the quicksort algorithm. In quicksort algorithm, we select a pivot element and we position the pivot in such a manner that all the elements smaller than the pivot element are to its left and all the elements that are greater than the pivot element are to its right. The element to the left and right of the pivot from two separate arrays. Now the left and right elements are sorted using the same approach. This process continues until the subarray consists of a single element. When this situation occurs, the sorted elements and we can merge the elements to the required array. Moving further, let us know how to select a pivot element. There are four common ways of selecting a pivot. One can use any one of the following methods. The first one is pick the first element, and the second option is pick the last element, and you can either pick a random element or pick the median element. Algorithm for quicksort. The quicksort algorithm consists of two different algorithms, one for partitioning the array according to the pivot and one for actual sorting. Let us look at both algorithms one by one. Let us first discuss the algorithm for partitioning the array. Step 1. Take two elements low and high. Make low store the starting index of the array. Step 3. Make a high store of the last index of the array. Step 4. Take a variable j and initialize it to low. Step 5. Take pivot as a last element in the array. Step 6. Traverse through the entire array using variable I and compare each element with the pivot element. Step 7. If array of I is less than pivot element, then increment j and swap elements as position j and I. Step 8. Increment I by 1. Step 9. When the loop terminates, return j minus 1. The value returned by partitioning algorithm gives us the correct position or index of the pivot in the array. What is meant by correct position is that all elements preceding the pivots are smaller than the pivot and all the elements after the pivot are greater than it. Let us now look at the sorting algorithm. Step 1. Take pivot as the last element in an array. Step 2. Find the correct index of the pivot using the partition algorithm. Step 3. Recursively call quicksort on the left subarray. Step 4. Recursively call quicksort on the right subarray. Moving on, let us see how the quicksort algorithm works. To understand the working of quicksort, let us consider the following example. Let the elements of the array in an unsorted order to make it more clear in understanding the concept. The elements of the array are as follows. You can see that there are elements which are in unsorted order, which is that is 24, 9, 29, 14, 19, and 27. In the given array, we are considering the leftmost element as a pivot element. So in this case, array of left is equal to 24. So array of right will be 27 and array of pivot will be 24. Since our pivot element is at the left of the array, the algorithm starts from right of the array and move towards the left. As you can see in the above diagram, now the array of pivot element is less than array of right. So algorithm which is at right moves one position forward towards left. That is, you can see in the below picture. Here array of left is equal to 24 and array of right is equal to 19 and array of pivot will be 24. Now as array of pivot is greater than array of right, the algorithm will swap array of pivot element with array of right element and the pivot moves to the right. This is illustrated as follows. As you can see in the above picture, now array of left is equal to 19 and the array of right will be 24 and array of pivot will be also 24. Since the pivot is at right, so algorithm starts from left and moves towards the right. Here, array of pivot element is greater than array of left element. The algorithm moves one position to the right as given below the example. Now array of left is equal to 29, array of right is equal to 24 and array of pivot is equal to 24. As array of pivot is less than array of left element, we swap array of pivot and array of left. So now the pivot is at the left, that is as shown in the below figure. Now, as the pivot is at the left, the algorithm will start from right and move towards the left. Here, array of left will be 24, array of right will be 29, array of pivot will be 24. As array of pivot is less than array of right, the algorithm would move one position to the left. Now, array of pivot is 24 and array of left is 24 and array of right is 14. As array of pivot is greater than array of right, we swap array of pivot and array of right, and now the pivot is at the right. That is as shown in the below figure. Here array of pivot is 24, array of left will be 14 and array of right is 24. Since the pivot is at right, the algorithm will now start from the left and move towards the right. As you can see in the below, I mean the above picture, now the array of pivot is 24, array of left is 24 and array of right is also 24. Left and right are pointing to the same element, which is pivot element. This point represents the termination of the procedure. Now the element 24, which is the pivot element, is present at its exact position. At this point, all the elements that are to the right side of element 24 are greater than it, and the elements that are left side of the element 24 are smaller than it. Similarly, the quicksort algorithm is applied separately to the left hand and the right subarray. After sorting, the resultant array would be as shown in the below picture. Coming to the time complexity part. Time complexity is of three types. One is best case, and the other is average case, and the third one is the worst case. First, we'll be talking about the best case time complexity. In quicksort, the best case is said to occur when the pivot element is the middle element or is the near middle element. The time complexity of quicksort in the best case is O of n into log n. You can see the derivation of best case time complexity. Coming to the average case time complexity. The average case occurs when the element of array are in jumbled order, that is not properly ascending or not properly descending. In this case, the time complexity of the quicksort algorithm would be O of n into log n. As you can see below, there is a derivation for average case time complexity. Coming to the last one, worst case time complexity. In quicksort, the worst case will occur when the pivot element is either the greatest or the smallest element of the array. Suppose that the pivot element is always the last element of the array. The worst case would occur when the given array is sorted already in an ascending or descending order. The time complexity of quicksort in the worst case is O of n square. As you can see, the derivation is given below the worst case time complexity. So the final will be T of n will be equal to O of n square. Conclusion. Quicksort is widely used sorting algorithm known for its efficiency in most cases. Understanding its time complexity helps in assessing its performance and optimizing it for better results. The speed of quicksort makes it one of the most important sorting algorithms. This is why one when learning sorting algorithms shouldn't skip over this algorithm. Thank you everyone. Subscribe for more.